learners. Getting into this molecular orbital theory. I love this stuff. This is so cool. More continuation of things from general chemistry. And we're going to put a little CHEM twist on it. All right. So let's get into it. And so we're going to start our discussion of molecular orbital theory by describing the H2 plus molecule. So that's about as complicated of a molecule as we can do, okay? And so let's set it up. So here is our physical picture. So here we have one hydrogen atom. Oops. We've got one hydrogen atom right here with a positive charge in the center. Call it atom A. And then here we've got another hydrogen atom. We'll call it atom B. And that, of course, also has a positive charge right here. And it's sharing, both of these atoms are sharing one electron. So it's the H2 plus molecule. And so we're doing H2 plus because, remember, electrons will interact. And adding that extra term into our operator makes it impossible to solve without approximations. Okay, so we start by first describing H2 plus and make approximations from there. Okay, so here is our Hamiltonian operator, right? We know that we've got a kinetic energy term, and it's the same as what we've seen before, negative h bar squared divided by 2me times del squared, where we know del squared is the second derivative squared in terms of xyz or in terms of r theta phi, right? And then now we also know that we've got a potential energy term right there, which you can see is listed right here. And it's entirely due to Coulomb's law, okay? So our potential energy operator, you notice here that there's no angular momentum terms in here because as it turns out, these two nuclei are in close enough proximity to each other that it's Coulomb's law that dominates, okay? And so we notice here that we've got a 1 over Ra1, and so that's going to be the distance, right, between the electron and atom A. And we've got an Rb1, that's going to be the distance between also the shared electron and atom B. And what you'll notice here is, right, there's a negative term right there, okay? So when that distributes through to this Ra1 or Rb1, those are attractive terms, right? The electron is attracted from its opposite charge, right? Negative and positive, it's attracted to atom A, but it's also attracted to atom B. And then now notice we've got this negative 1 over R term, right? So when I distribute that through, I've got a negative and a negative sign. I'm going to get a positive E squared 4 pi epsilon naught over big R, which you can see right there. And that is the repulsive term between the two positively charged nuclei, okay? So there's three kind of effects going on here, right? There's the repulsion of the two nuclei. There's the attraction of the electron to atom A, and there's also the attraction of the electron to atom B, all right? And so, of course, as we do, right, we would solve the Schrodinger equation for this situation. And a solution does exist for this. However, it's complicated, and it can't be extended to polyatomic molecules or ions. So more than just our simple linear molecules, okay? So several approximations have to be used. So the main approximation that we're going to discuss in MO theory is known as the LCAOMO. And that is the linear combination of atomic orbitals to form molecular orbitals, okay? So, and it goes like this. We're going to come up with a wave function that we're going to call psi plus minus. And we're going to call it plus or minus because we don't know which is which with arbitrary precision. And Pauling says we have to change the sign of the wave function if we change its label. So we include a plus minus there because we have to look at both solutions. We have to look at the positive solution, so psi plus, and we have to look at the negative solution, psi minus, which is achieved, psi plus is a normalization constant times a plus b. That's the linear combination of atomic orbitals. And of course, psi minus is then the normalization constant n times a minus b. Okay. Well, so I'm using a very simple nomenclature here. Okay. And just to give you all of the nomenclatures that are used, A is a wave function, so I'll put the ket around it. Okay. And that's the same nomenclature as chi H1SA, so that is still a wave function. So chi is used in place of psi. I don't make this stuff up. I'm just the messenger. And of course, hydrogen, 1s electron, and A, meaning that it's atom A. And this should all look familiar to us, right? This is our hydrogen ground state wave function, right? Hopefully you've got this tattooed on your forehead by now. Okay, so then B, right? We know that we can come up with a B wave function. And same nomenclature as just calling that chi H1SB. And then, of course, it's going to be the same wave function. But now keep in mind, look, where these are different are in the radii. Okay? And, of course, using our polar spherical coordinate system, if we arbitrarily define RA1, then we can define RB1 in terms of RA1 and in terms of R. Okay? And so again, we've made this lovely triangle so we can follow Pythagoras to get this coordinate system. Okay? So of course we would plug this equation into right here, and we could just leave this as RA1. And when we put this whole thing together, we will have our wave function in terms of, just one of these radii. That's all we would need to specify. And of course, the internuclear distance. All right. And once again, we're going to define this internuclear axis as the z-axis, just like in valence bond theory. So if I was setting up my coordinate system here in Cartesian space, right, the axis between the two nuclei is z, and one of these is x and one of these is y. Okay? And just like we did for valence bond theory, there's going to be a convenience of converting this to a Cartesian coordinate system. And I'm just going to draw that up really quick right here. Okay? So we can do, actually, you know what? I'm going to do that later, so because that's going to be connected to the Mathematica assignment that you can see that I've got right in front of me. But I don't want to confuse that issue, so we'll bring this in after the fact. But what I want to show you, what you can see that I've got right away here. Look, I've got my A1s wave function. There it is as a function of RA1. I've got my B1s wave function. I kept it in terms of RB1 because in Mathematica I can do that, right? Okay. But I could have also made it in terms of RA1 if I want. And what I want to show you right away here, I'm looking at the, let's advance the slide. So I'm looking at the psi plus state. And of course, we know that, let's see here. We know that the square of the wave function is going to give us the probability distributions. And so here I've got that written down. I've got n normalization constant times A1s plus B1s. And then here on my plot, I'm looking at psi squared. So let's walk through this and I'll show you what the result is on this manipulate. So we know what n squared is, right? That's our normalization constant. I'm just going to say norm. And so this came from foiling, right? So we'll say that psi plus was n times a plus b. And so when I square this whole thing, right, I square that and I square that, I get this, first, outside, inside, last. A squared plus B squared plus 2AB. So A squared is the probability that the electron is confined to A. And so that's, right, just going to take on the pure 1s orbital, right? When I square this A function, that's just the 1s orbital, right, as we know it. B squared is the probability that the electron is confined to B. And so once again, that's just going to be, 1s orbital, okay? And now this 2AB, this is what we call the overlap density or the overlap integral. And this describes the enhancement of electron density in the internuclear region, okay? So according to MO theory, here's the concepts to know. Bonds form when electrons accumulate in regions where atomic orbitals overlap and interfere constructively. So this addition sign, right, these plus signs, those are going to give us constructive interference, as I'll show you momentarily, okay? And we know that a bond will form, according to MO theory, a bond will form if there is constructive interference in that internuclear zone between the two nuclei. Okay? Electrons can interact with both nuclei, which lowers the overall energy of the molecule relative to the energy of the individual atoms, and we'll see that soon. A sigma orbital is a bonding orbital, which is also called psi plus in this simple example right here. And similarly, our sigma orbital, just like in valence bond theory, it's cylindrically symmetrical about the internuclear axis, right? And the molecular electron configuration for H2 plus 1 is given as 1 sigma 1. Technically, it's 1 sigma G1, and we're going to talk about what that extra G means momentarily. All right, so this is a look at my simulation right here. And so I've got this on a manipulate plot where now I've got my two 1s orbitals 2.5 angstrom apart. So this is all in scales of angstrom. And so now when I manipulate big R, I manipulate it to be smaller. I'm manipulating the two nuclei to get closer together, okay? And we have to accept, this is only a one electron system. So this is kind of viewing this as a superposition of the electron density being centered on both atoms, okay, which is an approximation. Because really we know when I form an H2 molecule, I've got an electron and an electron in each atom. Okay, so that's where this is an approximation. That technically this is H2 plus, but we're really going to use it as a model to describe H2. Okay, and so now as I get these closer together, something really cool starts happening. Look, you can start to see shared probability. That's what this, so the blue color right here is 0. So this in this contour plot, my blue color is where the wave function takes on a value of 0. So wherever it takes on a value of non-zero, you can see where it's increasing, right? That means that it's having larger probability. So you can see right now, the probability is still mostly centered on the two individual nuclei. But as I get these close to each other, maybe about an angstrom or less, look at that. There is now probability. There's now electron probability existing between those two nuclei. And here we have created H2 plus in Mathematica, which is really cool. And of course, my model also doesn't have any kind of like repulsion. So I can actually just put these right on top of each other without any consequences in here. So I haven't built in anything about the potential energy on this situation, right? And that's the approximation of the LCAO, the linear combination of atomic orbitals to form molecular orbitals, all right? But the sweet spot, as it turns out, for H2 is right around an angstrom or so. And there it is. That's my sigma bond, which is really cool. Okay, moving on. So the psi plus squared is the bonding orbital. It's the 1 sigma bonding orbital, okay? And so you can see from my simulation, right? Regions of constructive interference. And I showed you this picture in valence bond theory, so this is still applicable, right? So you can see that constructive interference right there owes to that sigma bond forming. And the way we view this overlap integral, this 2ab, this function describes that enhanced electron density that we see right there, okay? And on this picture right here, each of those dots represents the nuclei. So I'll put positive charges there next to them, okay? Well, the psi minus state is the antibonding sigma orbital, okay? And so for now, I'm just gonna call that a 2 sigma, but we're gonna put a more specific set of nomenclature to this, okay? And so now you notice there's still an a squared plus a b squared, but now there's a negative 2ab. And that makes it the anti-overlap integral. And so now if you look at this here, in the anti-overlap integral, one of these takes on positive values and one takes on negative values. So when they get close to each other, they destructively interfere. And so now there's no electron density between the two nuclei. Rather, the electron density is pushed out away from the internuclear zone. So it literally is an anti-bond. It's not going to make a bond. And on my model here, if I keep scrolling down, you can see there I've got it, n normalization constant times a minus b, okay? And now this is really cool. If I go to that magic about 1 angstrom or so, look at that. They don't want to bond, and you can almost see that they're like repelling each other, even though technically I don't have that feature built in. This is all entirely from destructive interference, okay? And so this is pretty cool. So they don't form any kind of bond at all. All right. So what do the energy solutions look like for these things? And so I'll remind you, right, even though we're not going to do it, we're not going to go through the solution to this, right? If I were to take the Hamiltonian and operate on, psi plus, then I'm going to get the E plus, the energy of the bonding orbital, times the original wave function. And then, of course, over here, if I operate on the psi minus wave function, I'm going to get the E minus energy solution. And, of course, the original wave function, right? So we're not going to do it. As you can see, it gets a little complicated. But I am just going to show you some of these equations and how they manifest, okay? So we remember that psi plus is bonding, n squared, times the quantity, a squared plus b squared plus 2ab. And the solution for this is pretty cool. So look, it's E plus, and as an intercept, right? So that means when R is, let's say, I don't want to say 0 because 1 over 0 is not well defined. When R is infinity, okay, let's look at it from that perspective. As R approaches infinity, so in other words, as these nuclei are, infinitely separated enough that they don't know that each other exists, okay? Well, if you were to follow through all of these solutions right here, so, and I think that I actually forgot to even mention that J0 on that very first slide, right? J0 is this collection of constants that we'll see quite often for Coulomb's law, E squared divided by 4 pi epsilon naught. Apologies for getting to mention that. So here's that collection of constants right there divided by R, okay? And so now if you look at the rest of these integrals, look, here's this J integral, which goes as the collection of constants times a squared divided by RB d tau. And that all ends up equaling the following. And the important thing to note is it's 1 over R, okay? S, this is the actual overlap integral. And this is why we call it the overlap integral, because it is literally the integral of a times b d tau, okay? And there's not a 1 over r dependence here, but there is an e to the negative r dependence. And that's going to be important in a moment. And then similarly, you can see this k, this other collection of integrals and constants, has this e to the negative r. And so what happens is as r approaches infinity, as the nuclei are very far separated, all of these terms drop out, and then E plus approximately equals just the H1s energy. So in other words, when the two nuclei are really far apart from each other, we just get back the original hydrogen 1s energy, which is a good thing, right? And you can see on the antibonding, it goes the same way. As R approaches infinity, then E minus is approximately, it's approaching the EH1s, just the atomic energy, okay? EH1s, okay? And so, like I said, these solutions, right, this equation looks fairly simple, but remember, the J0, that's a big collection of constants. J is this entire solution right here. K is this entire solution, and S, of course, our overlap integral, is this entire solution, right? And so when we put all of those together, we, not quite just yet, so just describing what happens to this overlap integral, right? I talked about how we have the overlap and the anti-overlap integral. So we can really see that the value of S when the internuclear separation is 0, in other words, when the two things are right on top of each other, S is equal to 1. It's perfect overlap. And of course, that's not physically accurate because we know the two nuclei can't be right on top of each other because their nuclei would repel each other away. But like I said, that's why this is an approximation, all right? So the sweet spot for H2 is right around roughly about equal to a Bohr radius or so, okay? Wait, no, I take that back. It's roughly equal to 2 Bohr radii. So A0 equals 52.9 picometer, which is 0.529 angstrom. And so the bond of H2 is roughly 1 angstrom. So you can see this R divided by A naught, when it's right around 2, right, that's about 1 angstrom of separation between the two nuclei. And so for H2, our sweet spot is right there. So that's, about 0.6 or so overlap. And of course, the length and strength of a bond is dependent on this overlap, all right? So as we force the two nuclei to get farther apart, there's less overlap, right? You can see the overlap integral, the value of it decreases. And so as the value of the overlap integral decreases, of course, there's going to be less electron density between the two nuclei, which would be a weakened bond. Of course, as there's more overlap density in between the two nuclei, then that would indicate a stronger bond. Okay, there's more overlap. And so now what I want to show you, yes, here we go, the energy solutions, okay, for E plus and E minus. And for now, I just noted these as 1 sigma and 2 sigma, which you can see on the graph. However, when we're going to add in some extra details for our molecular term symbols, and so we're going to specifically call the 1 sigma bonding orbital 1 sigma G, and this antibonding orbital psi minus, in some texts it's called 2 sigma. We're going to call it the 1 sigma U, and I'm going to describe those soon. Okay. So this is a pretty cool graph. So it's showing you calculated energy solutions versus experimentally determined energy solutions. And they're both fairly similar. They're obviously different, but they're similar in their profile. And what I want to point out is they take on the functional form of a bound state in terms of the E plus, right? So we know that for all bound states, E plus should be less than 0. And you can see here's the 0 line. So there it is, okay? And what we also note here on this Y scale, look, this is written as E plus or minus EH1S, and of course divided by RH to normalize it. However, by taking this E plus minus EH1S, right, we're subtracting out that energy for hydrogen 1s. So what that means is, right, we talked about this R approaching infinity. So as R approaches these values way out here, so you can see that both of these are approaching 0. And that's because of the way this Y scale has been plotted, right? This Y scale is this E plus, minus the EH1S. So if we had not included that, we would not get this E less than 0 for all bound states. However, subtracting out that atomic contribution, we recover that boundary condition, that the energy is negative for all bound states. And of course, we can see whether we subscribe to the experimental method or the calculated method, there would be our sweet spot. And you can see, like I said, it's right around 1 angstrom. When this value is equal to 2 R over A naught is right around 1 angstrom or so. Because remember, A naught is 0.529 angstrom. Okay? And so we get this lovely bound state, right, where we would get a minimum energy corresponding to its bond energy and its bond length. And as we increase the distance between the two nuclei, our overlap integral decreases. So there is less electron density between the two, and we're just approaching the energy of a single bare atom. Okay. So what about the antibonding state? Well, as it turns out, this equation right here, and of course, right, if I subtract over the energy contribution right to the other side, like it says on the Y scale, then what I get here are what I will refer to as a repulsive state. Okay. So in other words, if you look at this, so these are the values, these exponentially decaying values. They're technically 1 over r squared. It's not exponential because it's a repulsion due to Coulomb's law, or not 1 over r squared, but 1 over r. So I should say E minus proportional to 1 over r. And so it just decays. So there's no minimum, okay? So there's no sweet spot where the electron is going to want to exist, right? So if we promote this electron all the way up and we're subscribing to our laws of thermodynamics, right, where this thing wants to minimize its energy, it's just going to keep going and going and going and going and going until we've got that anti-overlap, as I showed, where the electron density is pushed all the way out. So when we're going to start looking at graphs like this a lot, and when you see these, these Leonard-Jones types graphs that have this minimum, I want you to think of that as a bound state. So it's stable, it's bonding. That's what it means by a bound state. And when we see these curves up here, these just decaying states, I want you to think of those as repulsive antibonding states. So that's how we're going to be able to connect a bonding state and an antibonding state when we look at their energy profiles. Okay. So let's see here. So that's a good place to stop for this first video. I'll see you in the next one.